Okay, so first of all, thank the organizers for the opportunity to present this work here. All this will be joint work with Mark Mars. So this talk is going to be about thin shells and matching of spacetimes. So let me start from the very basic part. And let me introduce what a thin shell actually is. So thin shells are idealized objects introduced in general relativity to describe sufficiently narrow concentrations of matter or energy. And by sufficient, I mean that these concentrations can be assumed to be located on a hypersurface. Of course, depending on the causal character of the hypersurface, thin shells can be null, time-like, space-like, or mixed. And of course, thin shells possess their own gravity and therefore they affect the spacetime geometry. And in order to understand this effect and also in order to construct the spacetimes containing thin shells, one needs usually to consider two spacetime regions and then match them across a hypersurface in order to create a spacetime containing a thin shell. So for example, null shells have been proven useful for modeling infinitesimally thin concentrations of massless particles as well as impulsive waves. So let me briefly recall the matching theory a la more. So in this matching theory, one takes two spacetimes with differentiable boundaries, and then one construct a new spacetime by providing two things. First, an identification between the boundary points, and then an identification between the full tangent spaces on the boundaries, okay? And of course, given two general spacetimes, the matching between them will be in general impossible, which means that these two spacetimes need to satisfy certain conditions, which are well known to be known as junction conditions, which in particular impose that both boundaries need to be isometric with respect to their induced metrics. And of course, with this matching theory, one can construct a spacetime containing a thin layer with material content given by the jump of the on the extrinsic curvatures. But there exists yet another method which applies when the boundaries of the spacetimes to be matched are actually null hypersurfaces, and this is a so-called cut and paste method, which is slightly different. In this particular case, one considers a spacetime with Dirac delta distribution with support on a hypersurface, which means that in this case, the metric is highly non-regular, and therefore you cannot apply standard tensor distributional calculus to deal with this problem. So one proceeds in a slightly different ways. One first take light coordinates adapted to an hypersurface. Then one removes this hypersurface, which leaves you two separate regions. And then these two regions of the spacetime are reattached by imposing some reorganization of points on one of the boundaries. And this reorganization of points turns out to provoke a jump on the coordinates, which in turn is responsible for the appearance of the Dirac delta distribution on the metric. With this method, Penrose was able in the 60s to describe impulsive frame-fronted waves and spherically fronted waves propagating in the spacetime of Minkowski. And there are later works by for example, Griffiths, Podolsky, Saman, Steinbauer, and a big etc. of people who have tried to, who have worked on more complex spacetimes. So the main goals of this talk are actually the following. So our aim is to provide a fully abstract description of the matching problem, and this abstract means the same thing as in Mark's talk. We want a formulation of the junction conditions in a completely detached way from the spacetimes to be matched. And for that, we shall need to identify which are the necessary and sufficient conditions that allow for the matching in this new language. And once we have done this, we will identify the geometric objects upon which the whole matching depends. And this will be done for general causality of the boundaries. Then after doing this, I will focus on the null case, and I will provide the explicit expressions for the matter content of any null thin shell, in particular for the energy density, the energy flux, the pressure, and even the purely gravitational part. I will also analyze the case when given two spacetimes, you can match them in more than one way. and we will see what happens in this particular scenario. I will finally connect these results with the cut and paste constructions, and I will finish the talk with a particular example in the anti-de Sitter spacetime. And the framework in order for the prescription of these junction conditions at the astral level will be this formalism of hypersurface data introduced by Mark in the previous talk. So let me provide a very brief recall of this formulation. So as Mark has said, so you have this formalism of hypersurface data relies on two core notions, which are the notions of metric hypersurface data and hypersurface data. So you, on the one hand, have the metric hypersurface data, which basically encodes intrinsic information about the hypersurface. And in particular, in the null case, you want gamma to be degenerate, or in other words, you want the scalar n2, which is defined through the inverse of the tensor A, to be zero everywhere. And on the other hand, you have this notion of hypersurface data, which has this extra tensor field y, which basically encodes extrinsic information about the hypersurface. I will also define a point, an unnull point, as the point where n2 is different from zero, and I will call it null otherwise. And of course, the connection with the geometry of submanifold is done by these notions of embedded metric hypersurface data and embedded hypersurface data. And this requires the concept of rigging that Mark has also presented. So imagine an ambient space, you take a hypersurface, and then you take an everywhere transverse vector field along the hypersurface, and you, by requiring these conditions up there, so these conditions up there and this one, you basically construct, by picking a rigging and an embedding, you construct embedded hypersurface data. And as Mark has said before, so in the null case, this n2 equals 0, and therefore n, which is the vector field at the astral level, should be thought of as a null generator. Okay, and since the choice of the rigging is highly non-unique, there are 6 built-in gauge group within the formalism of hypersurface data, and we define the gauge group action as Mark has showed before. So you have that gamma is invariant, and you have these transformations for the remaining tensor fields. And some important, some remark I wanted to make here, and it is the following. So if you consider a non-null point P, then there exists 2 gauge group elements such that they leave the metric part of the data invariant. And this is, of course, the identity element, which in fact leaves the whole hypersurface data invariant. And the other element corresponds, for example, in the embedded picture, if you consider an embedded hypersurface and you take a rigging, then if you apply this gauge transformation, you are basically taking the reflection of the rigging with respect to the hypersurface. So these 2 gauge group elements leave the metric part of the data invariant. Here, gamma star is the inverse of gamma because you are at an null point. And on the contrary, if you consider a null point, then you only have the identity element as the one leaving the metric part of the data invariant, actually the whole hypersurface data invariant. And another important result is the following one. So if you consider null metric hypersurface data, and you take whatever function u and whatever covector theta, such that its action over n is different from zero, then you can always find a gauge group element such that L becomes theta and L2 becomes u. And that basically means that for null hypersurface data, you can always set L and L2 to be whatever thing you want. So I will use this later. So let me start with the actual matching problem. And in order for doing this, I will start by recalling the standard form of the junction conditions, and then I will take steps towards the abstraction of these junction conditions. So the usual junction conditions read as follows. You given two spacetimes n plus minus with boundaries n plus minus, then the matching between them is possible if and only if you can find a diffeomorphism phi between the boundaries, which is from now on called matching map. And you need to be able to find a pair of rigging vector fields, which are theta minus and theta plus, satisfying conditions 1. In particular, this condition means that both boundaries must be isometric, and you need this extra condition over the orientation of the regions, which basically says that one needs to have one region pointing inwards with respect to its boundary and the other outwards. So several remarks to be done here. First, if condition 1 holds for a matching map and a pair of regions, then you can also one can also change the region on one of the sides, and you will find the region, another region on the plus side in this case. So therefore, that means that you can always freely select the region on one of the sides. And the other important thing to be said here concerns the result by March, Senovilla, and Vera, which basically says the following. If you consider a non-null point P, and you assume that conditions 1 hold for a matching map phi, then if you pick a region on one of the sides, say the minus side, then you will find two solutions for the region on the other side with opposite orientations. And therefore, by suitably selecting the orientation of the region on the plus side, you will always ensure that condition 2 is satisfied. But on the null case, this is different because you only find one solution for the region, and therefore it could well happen that conditions 1 hold, but the matching is actually impossible. Another important remark here is that from conditions 1, if you are given a matching map and a choice of region on one of the sides, then you are able to construct fully the region on the other side, which means that the whole matching information is actually encoded in this matching map phi. So let me now take one step towards the abstraction of these conditions. So for that, I will consider an abstract manifold N. Okay, and I will assume that I have two spacetimes that can be matched, and therefore I can find a matching map phi, and I can find a pair of regions, theta minus and theta plus. I can construct two embeddings, phi minus and phi plus, from N to the plus and the minus side, and therefore I am able to construct two metric hypersurface data sets from the pairs phi plus theta plus and the pairs phi minus theta minus. And for doing that, I just need to impose these conditions here. So if I do this and I impose junction conditions in their standard form, what I get is that the matching requires that the metric hypersurface data sets that I have built are actually the same, which means that given two spacetimes, the matching problem can be understood at the abstract level as one only needs to find one unique metric hypersurface data that can be embedded on both spacetimes at the same time. And of course, you have these second conditions on the orientation of the regions, okay? Of course, since the abstract manifold N can always be adapted to one of the matching hypersurfaces, that means that one can always take one of the embeddings to be as trivial as possible, and therefore one can select freely the region on one side and also the embedding on one of the sides, in this case on the minus side. And that basically means that all matching information is now contained in the other embedding. And of course, the continuous zero matching. Yeah. So so the whole matching information is now encoded in this phi plus embedding. And of course, the junction conditions impose that the metric part of the data coincide, but the extrinsic part of the data does not need to coincide, and therefore the matter content of the shell is going to be given by this jump on the tensors y, which of course are defined from the matching regions and the embeddings. And let me now provide the full abstract description of the matching problem. So the key part of this construction is that we want to construct two data sets over which we have full control. And in order to get this, what we do is to, again, consider two spacetimes. We take two regions, L plus and L minus, which are a choice, and therefore we know completely these two vector fields. We also make a choice of two embeddings, iota minus and iota plus, which are completely known. And this particularly allows us to construct two data sets, which are which will be embedded on the plus and the minus side from the pairs. By choosing this pair of embedding rigging on one side and the other, we can construct the data set D and the data set D hat. And now the idea is to find conditions on these data sets for the matching to be possible. So it is fairly clear that if we want to match these two spacetime, then since there must exist a matching map phi, that means that I need to require the existence of a diffeomorphism phi of n onto itself. That is quite obvious. And we need yet another condition, namely, if you remember from the previous picture, we need to somehow embed the same metric hypersurface data on both spacetimes. And therefore, we need to somehow compare these two data sets at the same point. So if we take, for example, the data set d hat at a point phi of p, and we pull it back to the point p through phi, then what we need to ask is that these two data sets are actually the same, and being actually the same at the level of the hypersurface data is basically that they are related by a gauge transformation. So that's what is imposed here. First, we need to require the existence of a diffeomorphism phi from n on n. And we also need to require that there exists a gauge group element such that these three conditions hold, which means that these two data sets are basically the same. And in order to translate the condition on the riggings, on the orientation of the riggings, we basically go to the vector fields L minus and L plus that we have defined, we have chosen. And then what we get is that, okay, so it is quite easy to compute that the rigging, the matching rigging with which L minus is identified through the process of matching takes this specific form, where T is tangent to the boundary plus. And therefore, the orientation of this vector field is basically given by this product here. And therefore, what we need to ask is that the vector fields L minus and theta prime L plus, and here theta prime is constructed from the gauge parameter set that is obtained in the previous condition. Then these two vector fields must have suitable orientations. Okay. And now I can go back to this thing of having two gauge group elements leaving the metric part of the data invariant in the non-null case. In order to recover the fact that condition 2 can always be fulfilled in a non-null case, we can think again of this fact. So that means that if I am in the non-null case, if I am able to find a gauge group element satisfying condition 2, then by this, since I have two gauge group elements will leave the metric hypersurface data invariant, then I can always find a gauge group element for which set has the opposite sign, and therefore condition 2 is always fulfilled if I make the right choice. And in the null case, again, this is completely different, and therefore, since I only have one unique gauge group element, then it could well happen that this condition is satisfied, but the second no, and therefore the matching is impossible. So at this stage, we now agree that matching amounts to embed the same metric part onto spacetimes, and that the extrinsic part of the data does not need to coincide. And therefore, we can codify a thin shell in a pair of data sets with the same metric part, okay? And since the metric part of the data is the same, then the gauge transformation of the jump of y, which defines the matter content, which determines the matter content of the shell, transforms trivially under a gauge transformation. And it is also a general fact that one can define an energy momentum tensor of a thin shell. This was done by Langtos in the 20s, Israel later, and Mars in 2013. So you can introduce this tensor field, which actually coincides with the energy momentum tensor of a thin shell. And the reason why we know that this tensor is actually the energy momentum tensor of a thin shell is that it, of course, has the symmetries of an energy momentum tensor. It behaves well under a gauge transformation. It may seem strange that the tensor tau changes under a gauge transformation, but this is a consequence of the fact that tau is a density, which means that it is actually tau times the volume form, which must be gauge invariant, and it does. This is also proven in March 2013. And in fact, this tensor field coincides with the classical energy momentum tensor in the non-null case, when you basically take as region the normal vector with norm equal to plus minus 1. Okay. So some important remarks to be done here. When you consider the non-null case, then tau requires all components of the jump of y to be constructed, and therefore tau equal to 0 means jump of y equal to 0, which means that you have no shell. But if you have n2 equal to 0, then you do not need actually all the components of y to construct the tensor tau, and therefore tau equal to 0 does not necessarily mean jump of y equal to 0, and therefore you can have a shell even with vanishing energy momentum tensor. And in order to see this, I have written this expression here. So in the null case, you can decompose the energy momentum tensor in these components. So you find a function rho, which is basically the p trace, and this p is related to the metric hypersurface data, if you remember. So it's the p trace of the jump of y. You find a function p, which is the nn part of the data, and you find this vector field j. So in fact, this decomposition allows you this decomposition suggests that rho is actually the energy density of the cell, p is the pressure of the cell, and j is the transverse energy flux of the shell. And it is easy to see that if one decomposes the jump of y in a p traceless part and a p trace part, then the p traceless part does not contribute to the energy momentum tensor, and therefore it is that part who gives you the purely gravitational content of the shell. And I have written there in a fairly general basis, so that you can see that it only depends on the metric part and the jump of y. So from now on, I will be restricted to the null case. So I will be studying null shells. So as I have said before, the matching conditions read as follow. This is the same as before, but we have said that when you deal with null metric hypersurface data, you can always set L, the one form L, and the scalar L2 to be whatever one form and the scalar you want. And therefore, this condition and this one will always be satisfied, and the important one is actually the first one. And in fact, gamma and gamma hat, which are constructed from the data sets D and D hat that I had talked about before, since these two tensors are gauge invariant, we can write this condition in this particular form. So what this is telling us is, okay, so pick two spacetimes, any two spacetimes you want, and construct metric hypersurface data, and then try to solve this equation. It could happen that you cannot find any phi solving this equation here, and therefore the matching is not possible. And it could well happen that you find a phi, and therefore the matching will be possible if the orientation of the rings is okay. And if you find such solution for phi, as we are going to see next, then you can obtain basically everything about the matching explicitly in terms of phi and the data sets you have constructed. For example, once you know this phi, then you can construct the explicit form of the gauge parameter set and v, which take this particular form, and which this set and v you can construct the explicit form of the ring on the plus side with which L minus is identified, and it takes this very simple form. And moreover, you can get the matter content of any null thin shell basically explicitly. Here, let me recall that U in the null case is basically the Lie derivative of gamma along n, okay? So everything here is explicit, And that result is key because this basically means that if one takes two spacetimes and finds a phi, then one automatically has the matter content of the shell that you can construct from these two given spacetimes. So this is the matter content of any null shell that one can construct. And some consequences of all these things, for example, this equation 3 here. So obviously the diffeomorphism phi is not completely restricted by this condition because first gamma bar in the null case are degenerate tensor fields, and moreover you can even find more than one solution to this equation, more than one phi, and therefore this condition does not fully restrict the map phi. On the other hand, it is important to know here that U and U bar are basically the second fundamental forms of the two boundaries that you are considering. And what this equation here, this equation 3 here is telling you is basically that it's giving you sort of an extra condition over the map phi. So imagine you have, so imagine that you have your two boundaries, and you know one point, and the image. So this point is within a null generator, and you know the image null generator to which this point is mapped. So when these two one forms U are both different from 0, then you are able to actually know the explicit map of the explicit identification of all points along these two null generators. But when both second fundamental forms are equal to 0, then you cannot determine this, and therefore you basically can send any point P along a null generator to whatever point along the image null generator on the other side. Okay. So in fact, for example, when you try to match two totally geodesic null hypersurfaces, then multiple matchings are actually allowed. And the next important result that I want to stress here is that one can compute the explicit expression for the pressure of any null thin shell. And the important expression is actually this one here, which basically says that the pressure is basically accounting for the differences between the, so here, kappa and kappa means surface gravity of the vector fields by star n or n, which are all null generators. So the pressure basically accounts for differences in the acceleration when moving along a null generator on one side and on the other side. And this is also interesting. So let us now consider the case of more than one matching. So in this particular scenario, what I'm going to do is actually I will consider that two matchings are possible. So we will consider again two spacetimes with boundaries, and I will assume that two matchings are possible, and I will also assume that one of the matching is fully known, which means that I completely know the matter content of the shell associated with one of the matchings, and I know a pair of readings. In this case, I have called them theta and theta hat plus, and so everything is known. Therefore, if I know one of the matching, it is quite easy to set both data sets D and D hat to be actually the same. Remember that matching amounts to embed the same metric hypersurface data into spaces. So it is quite easy to get into this, and therefore I can transform the junction conditions into these three conditions here. I have said before that these two conditions are less important because I can always find gauge group elements which guarantee this. So the core conditions for the core condition for the second matching, which has its associated map phi, is this one here. So in that case, it is quite simple to obtain the relation between the matter contents of the matching, say the matching 1 and the matching 2. And this is the explicit form here. Curly y is just a tensor field given in terms of known quantities, because this y hat is constructed from the data set d hat. So everything is known here. And therefore, you easily get a relation between the matter contents of two different matchings. And therefore, that basically means that, so this expression is actually key also because this basically means that if you can find a match, if you know that more than one matching can be performed and you can find one matching, then you automatically have everything, all possible matter contents of all possible shells that you can generate by matching the same two spacetimes. Okay. So now let me connect these results with the cut and paste constructions. So all the results before apply in the context of cut and paste constructions, with the peculiarity that in a cut and paste construction, you are basically matching two regions of the same spacetime. And therefore, you always know that there exists one matching, namely the no-shell matching, which makes that you can always take the same regions on both sides and a trivial matching map. And then you basically get no-shell, and this equation here, down there, basically I can remove this part here and I come into this, okay? So if that's the case, that you take a spacetime and you separate it into regions, and it turns out that more than one matching is possible, then this expression here basically tells you all possible matter contents that you can get from a cut and paste construction in which more than one matching is possible. And this is all done by at once, okay? So by simply solving this equation and finding all the phi's, which may be more or less difficult, but okay, then you can compute at once the explicit form of any pair of regions identified in its matching all possible matter contents, and explicit expressions for the energy density, the energy flux, the pressure, and the purely gravitational part of the shell. So let me now particularize all these things for one spacetime, one concrete spacetime, namely the anti-de Sitter spacetime. So here I have taken coordinates in which the metric is conformally flat. So here GMK is basically the flat metric. And I have two regions, namely the U positive and the U negative regions of this particular spacetime. Lambda here stands for the cosmological constant, and the boundaries of the spacetimes are U plus minus equal to 0. And they are in fact totally geodesic, which means that we are in this case, and therefore multiple matchings, actually an infinite number of matchings are possible. And we have full control over one of the matchings, which is basically the no-shell matching. And therefore, it is quite easy to construct metric hypersurface data, which takes this very simple form. Here mu is the conformal factor, and the y takes this explicit form. And here lambda and y are coordinates along n, such that lambda is a degenerate coordinate. And therefore, it is quite simple to get into these expressions for the energy density of the shell, the energy current of the shell, and the pressure of the shell. In particular, if you, for example, try to study or try to recover the results from the Minkowski spacetime, then you only need to set lambda to be equal to 0, and therefore mu is equal to 1, and then you get very simple expressions for these three quantities here. And here one can see how this pressure accounts for the compression of points on one of the boundaries, because basically so if you have one boundary and you have the other boundary, basically you take a null generator, and basically this H is telling you at what height is the image of this point. So basically derivatives, second derivatives of this function H, that is usually called the step function, are ruled by the pressure, and therefore it tells you how the points along a null generator are compressed on one of the sides. So let me conclude the talk. In this talk, I have provided a fully abstract geometric picture of the matching problem. We have codified explicitly the matching information in terms of a diffeomorphism phi of n onto itself. And for the case of null boundaries, we have derived explicitly the matter content of any null shell. We have analyzed the case when multiple matchings are possible and provided explicit expressions for that case. We have connected the results with the cut and paste constructions, and we have even provided a particular example of this. That's it. So thank you very much for your attention.